This is a discussion for experiment 26, which is the kinetics experiment in Chem 1B. So we're going to do a couple things in this experiment. We want to determine the rate law for a reaction. And the reaction that we want to determine the rate law for is the reaction of iodide with bromate in acidic conditions to form iodine, bromide, and water. It's a redox reaction, and the balanced reaction is as follows. 6 moles of I- aqueous plus 1 mole of bromate aqueous plus 6 moles of H+ aqueous yields 3 moles of I2, which is iodine, and that's aqueous, plus a mole of bromide aqueous, and 3 moles of liquid H2O. So we can write the rate law for this reaction as rate equals K, the rate constant, times the concentration of I- to the X, concentration of BrO3- to the Y, and concentration of H+ to the Z power. So in part 1, we will run a series of trials in order to determine X, Y, and Z, which are the reaction orders for each of those reactants. So part 1, determine X, Y, and Z, the reaction orders for our rate law. Once we have that, then we can determine the value of K, which is the rate constant, which is a constant at a given temperature. So in part 1, we will be doing the experiment at room temperature, which should stay pretty constant. In this experiment, we also want to investigate the temperature effects on rate and the rate constant. So how does changing the temperature affect the rate as well as the rate constant? And we will also determine what's called the activation energy for that reaction of iodide plus bromate in acidic conditions. Okay, so I'll talk about the activation energy a little bit later in this discussion. So this is done in part 2. So in part 2, we will change the temperature and see how that affects the rate and the rate constant, and then use that data to determine the activation energy for the reaction. So I'm going to go ahead and write out the reaction of interest in this experiment. So this is the one where we are looking at the redox reaction that is 6 I- plus 1 BrO3- plus 6 H+ going to 3 I2 plus a bromide Br- plus 3 H2O. All right, so one way we could write the rate for this reaction is we can look at the change in a reactant over the change in time. So let's think about the change in bromate over change in time. And I'm going to use a negative sign, negative delta BrO3- over delta T. So we always get a positive rate because bromate should be decreasing. So somehow we need a way to determine when a certain amount of the bromate has been used up, because we need to know how much is reacting to figure out what the rate is. So in order to do this, we need to use linked reactions. So we're going to use a linked reaction, and this linked reaction I'm going to call reaction 2. And essentially the I2 that is created in reaction 1 will react with another reactant added to our mixture, thiosulfate, and that will give us I- iodide, and it will give us S4O6 2-. So in this reaction, our S2O3 2- is the limiting reactant. So when it's all used up, a third reaction is going to occur. So a third reaction occurs here. And that third reaction is I2 created from reaction 1 reacting with starch that is also added to our reaction mixture to produce an I2 starch complex, which is blue. So this is a test you may have done in biology before. Iodine and starch form a blue complex. Both reactions 2 and 3 occur very fast. They're immediate reactions. So as soon as any I2 is produced from reaction 1, it will either react with thiosulfate or starch. So our data in this lab is we're going to mix together our reactants and use a stopwatch to time it until it turns blue. So our data is just time and temperature. Okay, I've rewritten our 3 reactions that will occur in our flask on this new slide. And so we are going to need to determine the rate law. In order to do that, we need to calculate the rate of the reaction. And the rate of the reaction we can write as the negative change in bromate over the change in time. So we could do some stoichiometric calculations in order to figure out that change in bromate. We know our initial bromate concentration, and we could calculate how much is left over after our solution turns blue. Okay, so we know that the thiosulfate, right, is the limiting reactant. So we could calculate the amount of I2 that it reacts with in reaction 2, and then relate that back to the stoichiometry in reaction 1 of the I2 and the bromate. So we could do those stoichiometric calculations. Or we could just use an arbitrary value for the amount of bromate that reacts and just make it easier on ourselves. Right? We know we can do it. We all passed Chem 1A, so we can do those stoichiometric calculations. So we can just use this arbitrary value since the amount of bromate that reacts when the solution turns blue is constant. It would be a constant value, okay, because the thiosulfate, is the limiting reactant, which it's a constant amount of limiting reactant. So I think you'd want to do it the easier way. So I'm going to call it the relative rate, and I'm just going to use the arbitrary value of 1,000 over the change in time, and that change in time is going to be the time it takes to turn blue. And when it turns blue, a constant value of bromate has reacted. So our units for our relative rate are just going to be in seconds -1, or 1 over seconds. Okay, so part 1, right? We're determining the rate law. We're determining those exponents, x, y, and z. So we are going to use a ratio of rate laws to do this, like we did in class, right? We're going to use that ratio of rate laws to determine those reaction orders, x, y, and z. So we would take rate for, say, reaction, we'll call it A, or trial A, divided by, and it's the relative rate, remember, so it's the relative rate, so we're just using that arbitrary value. So relative rate of trial A, for example, over relative rate of trial B, for example, and then that's equal to K times the concentration of I minus to the X power for trial A, times concentration of bromate to the X to the Y power for trial A, and concentration of H plus to the Z power for trial A. And divide that by K, I minus to the X power for trial B, bromate to the Y power for trial B, and H plus to the Z power for trial B. So if we keep the bromate and the H plus constant, it along with K will cancel, or those values along with K will cancel, because K is a constant, and if we keep bromate and H plus constant, we can then solve for X. And then we would need to repeat that. So we'd have to use 2 more trials where we cancel out the I minus and the H plus to solve for Y. And then we would need to use another 2 trials where we would cancel out the I minus and the bromate to solve for Z. Of course, in order to solve for X, Y, and Z, we need concentrations of I minus, BrO3 minus, and H plus used. So we are mixing things together. So whenever we're mixing, we're going to use our handy dandy MCVC equals MDVD calculation. So in the lab, will see the concentrations of those solutions and the amounts used in each mixture. And every single mixture has a final diluted volume of 25 mils. You can ignore the 3 drops of starch that are added, right? So we're just adding up all the volumes of the other substances and it comes out to 25 mils. Just ignore those 3 drops of starch. So in part 2, as I mentioned earlier, we're going to look at the temperature effects on rate and the rate constant, as well as determine the activation energy. So what we'll do is we're going to repeat mixture 1. We're going to use the tables in our lab to make up mixture 1 at 4 different temperatures. So we want 4 different temperatures total. So the temperatures we want around 0 degrees Celsius, around 10 degrees Celsius, around 20 degrees Celsius, and around 40 degrees Celsius. Well, room temperature should be around 20, so you can use your part 1 data for mixture 1 here. So we really have to do it 3 more times. So 0 degrees, we're going to use an ice bath. 10 degrees, we'll use a cold water bath. And 40 degrees, we'll use a hot water bath. So we'll perform our reactions at those different temperatures for mixture 1. So we'll record the actual temperature. So it might not actually be 0, it might be 1 degrees or 2 degrees, 10 might be 9 or 11, so on and so forth. So we will actually record the temperatures of the solution. So here's a question. Will the reaction be faster at 40 or faster or slower at 40 degrees C? So if we compare it to 0, 10, and 20, is it going to be faster or slower at that highest temperature? Okay, so what did you answer? Hopefully you answered faster, right? The molecules are moving faster at that higher temperature, right? They have more kinetic energy, so there's more collisions, and we can form more products. Okay, so we should expect a faster rate at 40 degrees. And K should be bigger, right? Our K changes with temperature, so if we have a faster rate, K is a bigger value. Okay, so we'll see if the data reflects those ideas. So part 2, right, we want to also determine the activation energy for the reaction. Okay, so what is the activation energy? I'm going to draw a potential energy diagram here with potential energy on the y-axis and the reaction coordinate on the x-axis. And we are going to think about our reactants starting at some potential energy and our products having some final potential energy. And we have to climb a hill to get there. And the difference between where the reactants are and the top of the hill is our activation energy. Okay, so that yellow arrow represents the activation energy. And the definition is it's the minimum amount of energy required for the reaction to occur. Okay, the minimum energy needed for the reaction. So I like to think of it like a high jump, right? In order for the high jump to count, the jumper has to clear the bar. Same here. If my reactants just make it to that potential energy, they're just going to come back down to reactants. If they make it to the top of the hill, then they will make their way to the products, right? So they have to overcome that barrier, and that's the activation energy. And we can determine the activation energy using the Arrhenius equation. And the Arrhenius equation is as follows. You actually used it at the very beginning of the semester in our graphing activity. But it is the natural log of our rate constant equals negative activation energy over R times 1 over T plus the natural log of A. So hopefully we notice this is in the form of Y equals mx plus b. So we're going to use a graph. Right, so y equals mx plus b. So if I make a graph of data, I want to plot the natural log of the rate constant on the y-axis, 1 over t on the x-axis. So here I'm going to draw that, where we have our natural log of k on the y-axis, 1 over t, and that's going to be 1 over Kelvin on the x-axis. And activation energy is always positive, right? It's the energy required. And we have a negative sign in the equation, so our slope is going to be negative. So we have a negative slope, and that slope equals negative E sub A over R. So R, of course, is 8.314 joules per mole Kelvin, or 0.008314 kilojoules per mole Kelvin, because you'll want to figure out the activation energy in kilojoules per mole once you graph your data. So you'll either use Google Sheets or Microsoft Excel to get your graph. Make sure you title the axes and give your graph a descriptive title. Now you are ready to go and look at the procedure video and get the data.